Hi. So this is a talk about interpretable machine learning. Today I'm going to be presenting some work on generating natural language explanations of representations inside learned neural network models. And we're specifically going to think of these representations as constituting a kind of language that we're going to call neuralese. And today we're going to build a system for interpreting neuralese by translating it into natural language. So first off, what do we mean when we talk about a language called neuralese? We're going to be focusing here on models that feature communication as a central component. So classically, if you want to build some kind of decentralized multi-agent communication system, say a fleet of self-driving cars, you have to design by hand the protocol that those cars are going to use for communicating with each other. Now, one of the things that we've learned in the last couple of years is that we can replace a lot of hand-engineered features in machine learning settings with general neural network machinery, and it turns out that you can replace hand-engineered communication protocols as well by just learning the details of those communication protocols from scratch. And what you get when you use sort of modern neural network approaches to these problems are models in which your agents are just sending around vectors of real numbers to each other that look like the hidden states of neural nets. So we really can think of this as being kind of neuralese language, but in particular it's a language that doesn't have any structure or any semantics that's visible or interpretable by a human observer. So what we'd like to develop today is some kind of technique that will take this uninterpretable language that's been learned in the context of one of these multi-agent systems and make it interpretable by translating it into natural language. Now, we could try to do this the way we do it in a normal machine translation setting. So what we're looking at right now is a standard noisy translation model, and what this equation on the slide says is that if I have my neuralese message, which we've drawn with a red 0, the best English translation of that message, which we've written with a purple A, is the one that is both assigned high probability a priori under some model of English, and also that people say in states of the world where our learned model is likely to produce the particular message that we're trying to translate. Now, in a normal machine translation setting, we would start with a data set of, for example, English and Spanish sentences, what's called a parallel corpus, where we get pairs of sentences in both languages that mean the same thing. And in this case, we could just read these two quantities that we need off of the corpus to build the translation model that we were looking at on the previous slide. The problem here is that we don't actually have access to parallel data. We can generate as many examples as we want of our learned agents talking to other learned agents, and we can go out and collect examples of humans talking to other humans trying to accomplish the same task. But there is no way to generate a parallel corpus of the kind that we typically need for machine translation because there isn't anybody who already speaks this language that we're trying to translate. So we're going to need to come up with some totally different way of finding English sentences that mean the same thing as sentences in this neuralese language. And to do this, we need to start by thinking a little bit about meaning. Now, in linguistics, one of the standard tools or frameworks for thinking about meaning is the notion of a truth condition. And this is really just a fancy way of saying that if I have an utterance like I'm going north, I can line up every possible state that the world might be in and walk along this list of states and mark off all the states in which I could truthfully say I am going north. And that collection of states now contains all the information that I need about the meaning of this utterance. Now, we can go a step further, and rather than making a binary distinction between states in which the sentence was trying to generate a meaning representation for as true or false, try to model meaning probabilistically as the distribution over states in which that utterance might have been produced. This takes us a little bit outside the formal framework that linguistics typically uses for modeling sentence meaning, but it's something that turns out to be well motivated from a bunch of other perspectives. So in cognitive modeling, what we call this, basically this distribution, is the belief that a Bayesian listener should compute about a speaker upon hearing an utterance. For people who work in kind of visualization for interpretable machine learning, we have yet a different name for what we're doing, which is just finding a set of training examples that maximally activate or correlate with a particular representation that we're trying to interpret. And what all this means is that this sort of notion of meaning representation that we're trying to embed inside our translation model is something that shows up in a bunch of other places in the literature, and this should give us some indication that we're on the right track. So, we're going to represent the meaning of an utterance by the belief that it induces in a listener. And the key here is that this can be true even for utterances that don't look like natural language at all. And in particular, we can construct a model of the belief that one of these learned agents should form about the other agent in the system upon observing one of these neuralese messages in a given state of the world. And we can translate that message into natural language, again, by searching in the space of natural language strings until we find one that gets some kind of human listener's belief as close as possible to the neuralese listener's belief. Now, concretely, again, we're going to represent these beliefs as probability distributions over speaker states given messages. We can try to match these distributions up using some measure of distributional similarity, and in practice it doesn't actually seem to matter that much which measure of similarity we use here. And so really the only thing we have to figure out at this point is how to actually construct these distributions in the first place. And the key thing here is that this is something that we can treat as its own self-contained machine learning problem. We'll build a model of agent beliefs, which is just a function from messages that agents send to distributions over speaker states, by just collecting examples of agents interacting with other agents and looking at the states in which they send the messages that they send. And similarly, even though we don't have access to a forward model, we can build a model of human beliefs using all the human data we have and just trying to reconstruct the states that our humans were in when they sent the particular messages that we saw them generate in the data. And the key thing to notice here is that we don't need parallel data to build either of these models. We can build our model of neuralese messages using only examples of our learned models interacting with each other. We can build a model of the meaning of natural language messages using only examples of humans interacting with other humans. Nevertheless, we now have enough to translate. And again, we're skipping over a lot of the technical details of the implementations of these models and the search process here, but the punchline is just that once we have these learned models, we can use them to find the most similar translations on the bottom here, like we were looking at on the previous slide. And what this gives us at the very end is a recipe for translating messages from this neuralese language into natural language without having ever had parallel data for the translations. So how might we go about evaluating the quality of a translation procedure like this? We're going to evaluate here on a couple of different tasks, and we're going to start by looking at the simplest possible example of a multi-agent communication problem, which is what's called a reference game. And the way these games work is I have some sort of speaker model on the left that's going to observe, for an example, an image, and it has to come up with some kind of representation of that image that allows a listener model on the right to distinguish the input image from some other distractor image that we've shown to the listener. And the way we're going to evaluate our translation procedure is exactly by putting our translation layer in the middle of one of these reference games. So we'll take a learned model that produces representations of images, and we'll translate those messages into English and hand those translations off to a human listener and ask the human listener to basically play the role of the listener model on the previous slide. And we'll see here whether our translation is good enough for this human listener to figure out what it is that this learned representation is actually trying to communicate. Now, if we start with a super simple version of one of these reference games, where the model is just trying to represent sort of colors in some color space, we get the translations that we're looking at on the slide right now. And if you look at these translations closely, you can actually learn something non-trivial about the representational strategy that's been learned in this particular model. And if you look here, it's mainly distinguishing colors on some kind of purple-green axis. So dark purple and light purple are represented in the same way, which we translate as magenta. Pale green gets translated as olive, and so on. But of course, this is mostly interesting in the context of more complicated representation learning settings. So here's the same technique applied to representations for image references. And you can see that the translations are actually picking out high-level abstractions for things like size and color in these learned representations of pictures of birds. If we look at how well people do when playing one of these reference games using images as input by way of a translation model, you can see that this belief-based translation procedure that we've described does better than a sort of naive statistical co-occurrence baseline, and in particular it does nearly as well as people do when trying to play this game with other people. And finally, to come back to this driving game that we used as a motivating example at the very beginning of the talk, We can look at the messages that this red car sent to the other blue car when it was trying to cross the intersection in various states of the world and for various configurations. And you can see that these translations that we're generating capture a lot of the essential semantics that we need for this game. And I really want to emphasize that these translations are generated without access to the underlying state of the world. We only see the message that this red car sent to the blue car when it was playing this game, but the translations are still capturing things like that the agent says done or at goal when it's close to the position that it's trying to reach. It says you first when it hasn't yet entered the intersection, and so on. In terms of actual game outcomes, the story here is basically the same. We can do much better than random chance, and a little better than sort of statistical baseline by really reasoning explicitly about the beliefs of humans and about the beliefs of learned models. So to wrap up here, this is really the only picture that you need to take away from this talk today. Sentences have meanings, and those meanings are reasonably well conveyed by probability distributions representing the beliefs that listeners form. And once we have some way of constructing these distributions, they serve as a convenient interlingua, a kind of intermediate representation that allows us both to translate between languages and even to work with things that don't look much like natural languages at all. And this in turn gives us a tool for interpreting learned representations inside sort of otherwise uninterpretable black box machine learning models. And that's all.